Thank you so much, Flip, for the very nice introduction, and thank you for inviting me here. Good afternoon, everybody. So I'm going to talk about something involving field theories and neural networks. And I learned that the audience is mostly working on dark matter and astroparticle physics. So please feel free to stop me at any point and ask me any questions if I'm speaking the formal field theory language too much. Please don't hesitate to interrupt if you have questions. So this work is very much motivated by my affiliations at Northeastern University String Theory Group and also the NSF AI Institute for Artificial Intelligence in Fundamental Interaction. Their whole motto is that we are going to bring in machine learning and neural networks and try to understand the fundamental interactions of our universe as much as we can. Independently, we were motivated to do something using quantum field theories for machine learning. And somewhere we found that there is a bridge between machine learning, or rather theoretical machine learning, the formulation of machine learning, and the definition of field theories that you read in the textbooks before you go into research. And using this bridge, you can go either way. You can study formal field theories, or you can study theoretical machine learning. So this is cool. We wanted to see how much we can get out of this for theoretical particle physics community. And I'm going to give you guys an overview of our results so far. This is based on 2 papers already out. The first one is the one you guys have been studying, which is about establishing the bridge between neural networks, which are backbones of machine learning, and quantum field theories on Euclidean background. Quantum field theories because we were not actually using the statistical definitions of various field theories. We were taking quantum field theory, language, framework, everything out of your favorite QFT textbook. And then for the sake of definition, we had to choose Euclidean background. And the third paper is our ongoing work. And this is the 50% of the talk. This is work with my advisor, Jim, Matt Schwartz at Harvard, and my 2 collaborators, Mehmet and Keegan. And here, I would talk about studying non-Gaussianities in neural network field densities in a controllable manner. That may be very interesting to some of you, because studying non-Gaussian features that come out of neural networks can be useful for training purposes, also for other reasons. Let's see. So for those of you who are not that familiar with neural networks, I will give a very brief introduction slide and just focus on the main points. Neural networks are the backbones of modern deep learning. There has been more progress, but for a long time, last 4 to 5 years, neural networks have been useful to us. So if you're a physicist and if you have seen the results machine learning has brought in for physics, one may be interested to study neural networks to some depth. So we asked some fundamental questions. How could neural networks benefit machine learning so much? And we found that mostly people were treating neural networks as black boxes. Or there was very deep computer science interpretations, which is abstract mathematics. As physicists, we did not understand more than 1 page. So we decided that what if we could understand this a bit more lucidly by using some of the theoretical physics frameworks, but not statistical physics frameworks, because to a group in string theory and theoretical particle physics, we wanted something that's a bit more closer to what we know, the language we use for our research. So we decided to bring in our language, that of field theory, or more stuffs from particle physics textbooks, and wanted to interpret this whole neural networks machinery in that framework. With that motivation, we will go ahead. A few more features. Very schematically, neural networks are giving us some functions. These functions take in real numbers from any dimensional input space and give out real numbers to any other dimensional output space. These are my notations for the dimensions. Now, if you study the densities of these outputs, they have similarities to field theories. That's where the bridge lies. There is some hidden structure in this function. And this hidden structure is determined by some choices of activation functions, which can be linear, sigmoid, ReLU, anything that you choose. It's up to us, controllable. There are some parameters, theta, which one can train to change over time. And by changing these parameters, theta, you can make a neural network give you outputs that you want. And there is this hyperparameter. It's called weight. It can be really small, or theoretically, it can be infinitely large. And in this variation of this hyperparameter, we get an output density that can be Gaussian or can be very highly non-Gaussian. By choosing the parameter distributions and the weight over here, we can control the non-Gaussian terms that describe the output density of the neural network. Schematically, it's a bunch of nodes, the circles, connected by edges in between. One of the common definitions, fully connected feed-forward network, has all the nodes connected with their neighbors. And you have seen many other examples of neural networks, I'm pretty sure, in cosmology and astroparticle physics applications. This direction, where you are just going across the number of nodes in a particular layer, and note that a particular layer is where the nodes are not connected to each other. They are connected with other nodes, but not to themselves, not to other nodes in this one layer. The number of nodes here is called the weight n. And this direction, where you feed in some real numbers and then get some output real numbers, this direction is called the depth. And every structure in between these layers of nodes are called hidden layers. Mostly probably because people treated this as black box. Everything was hidden. Here is a mathematical representation for outputs of each of these hidden layers. They are summed over the contribution of the nodes in a particular hidden layer. So if this one hidden layer has n nodes, then you are getting this output, which is right over here. And it's defined in terms of weights and biases associated with these nodes. And then in the next hidden layer, you are acting upon this function with a new activation function. And that new activation function happens at each of these nodes. You can choose different activation functions at each node or identical activation function. It's up to us. The point to note is, if you do not involve any training, but rather just define the neural network architecture by fixing the parameter distribution, fixing the choice of the activation functions, and the weight n, then you get an output which is a draw from some distribution. If you generate that output any number of times without any training, so you just create this neural network, and then just like tossing a coin k times, you are getting the output of this neural network on your computer k times. All those k outputs are getting drawn from same distribution. And the means, variances, statistical moments of those distributions get determined by the choice of the parameter distributions, activation functions, and this hyperparameter weight. So we decided that since we are getting a density over functions out of a neural network, we might want to study this using the Feynman path integral definition, where we treat field theories as distributions over fields. So following that, we said that we are going to construct a partition function for the neural network output ensemble. Output ensemble is just the collection of the neural network outputs many number of times. And all of this is without involving training. And the reason we are not going to talk about training right now is because we found that even without involving training, you can get field theoretic interpretation out of the neural network output densities. That was an interesting feature in itself. And then there remains the question, how can one study the neural network output density as a field theory when you involve training? That's a second order question. So we decided that this is something new that we know from field theory or particle physics too well, but machine learning community does not know about this. Now, if we bring in this notion, what happens? Do we simplify some features of the machine learning neural network black box? Do we benefit their community by giving them our knowledge? Turns out, yes, there are some benefits. Let me go over the punchlines, the big results we have so far. First, we found that the neural network output densities, or ensembles, are creating Euclidean field theories. There is no notion of time. And if you ask me what happens when we involve the training time of a neural network, I would say that that time would be very differently treated than the time dimension in actual quantum field theories. And I will explain why later. There is a particular limit of neural network output processes. By output process, I just mean that you are creating the neural network output many times, and altogether you're calling it a neural network process. This limit is called neural network Gaussian process. Here, the output density creates a Gaussian distribution. And this Gaussian distribution defines a free field theory through its partition function. On the other hand, by tuning the neural network architecture, you can move away from this Gaussian process. You can turn on some non-Gaussianities in the output density. And depending on how much you are moving away, which is controlled by your choice of architecture parameters and hyperparameters, you can get the neural network architecture to define weakly coupled field theory, where you get some perturbative corrections to the action, or you can get non-perturbative field theory, where you are clueless about what the action looks like. And we found, especially when we are in this non-perturbative field theory scenario, we can go back to the neural network architecture, study the structure of the partition, structure of the parameter distributions, choice of activation functions, and wait to decipher some of the properties like correlation functions, connected correlation functions, a series expansion for the partition function without knowing the action. So there would be no interaction terms, no quadratic free field theory term in that action. Nonetheless, you are expressing it in terms of some features of the neural network architecture. So that's an approximation to the field theory partition function. And something that's interesting in field theory community, locality. Locality is how much the distance between space-time points affect the field densities. It's a very rough way to put what locality is. But essentially, that's one of the features that we wanted to study using neural networks. Also, symmetries. So these features can be learned without knowing the action. And this is interesting because in general, when we are talking about field theories, one needs to have some control or some information on the action. Without knowing the action, it may be very difficult to study any of these properties. But neural networks showed us that this gives us this interesting toolbox called architecture, which lets you bypass the need for knowing the action. You can, and I will explain that in a bit. Yep. So kernel is just the two-point function, but you mean the correlation functions, right? I see. I see what you mean by a static theory, that there may be derivative terms. Yeah, so that's basically it, but you can also study symmetries and other features if you know the partition function. So theory is just as simple as giving it a path integral interpretation. You write down a partition function, you write down an action, and then using that, you predict as much as you can. So if you have the action, you can get the equation of motion. And those equation of motions correspond to the cases when the parameters of the neural networks are hitting the means of those parameter distributions, because equation of motion is the case when the probability of getting a particular field configuration is the highest. They don't use the exact term, but the times when the neural network output has the highest probability corresponds to when your parameter distributions themselves are at the peak. The parameter value is at the peak of each parameter distribution. Any more questions? All right, a brief set of motivations why we do this. So right now, we are actually trying to come up with neural network architectures where the free limit action is same as the known free field theory action, and the perturbative field theory limit actions are known interaction terms like lambda 5 to the power 4 terms and so on. And then we want to go to the non-perturbative section of those neural network architectures, and we will try to study the symmetries, correlation functions, and other properties using the architecture directly without knowing the action. So in this way, we would not need the neural network training or Markov chain Monte Carlo procedure to get the right field theory action from a neural network architecture. We will have a neural network architecture, and the output density itself will behave like the field theory that we want. There's an important feature. So these field theories are all statistical field theories. But in some cases, depending on your choice of architecture, the correlation functions, which are on Euclidean basis, Euclidean background, they may satisfy a set of axioms known as Osterwalder-Schroeder axioms. And in that case, it is possible to treat the Euclidean space in this whole formalism to have a corresponding Lorentzian background. So you have the neural network giving you a statistical field theory, but there is a corresponding quantum field theory where the background is no longer an Euclidean space, rather it's the Lorentzian background. So for that, you need to have certain kind of architectures. We don't have a first principle so far to produce those architectures, like give us a family of architectures that will show us quantum field theories corresponding to these. However, we do know what is the constraint. Given an architecture, you can check whether it gives you a quantum field theory or whether it fails to give you a quantum field theory. So we have done that. It's in the work of my advisor, Jim. And finally, when you combine these interesting neural network architectures where field densities are behaving, output densities are behaving like known fields, then you may be able to reproduce some of the scenarios similar to the known field theories like the standard model. Scenarios from our lunch discussion. So again, these are the two references, and please feel free to ask me questions about any of the papers. This was the first one with Jim and Keegan, and the second one on symmetries, studying the symmetries of these field theories without requiring knowledge on action, also with Jim and Keegan. And finally, the third work is on understanding how you get non-Gaussian terms in the neural network output densities and how you can study the corresponding field theories using the architecture in that case. This is work with Jim, Matt, Keegan, and Mehmet. So there are some other works as well between neural networks and field theories, establishing connections between them. And here are some references. I won't go into this right now, but if you're interested, please ask me later. Here is the outline. First, the NNGP, where you get the neural network output density, purely Gaussian. And it gives you a free field theory. I will discuss it briefly, and then go ahead to the case where the output density gets some perturbative corrections due to changes in the architecture. And in that case, you can write down a Wilsonian EFT description for that neural network. And thirdly, When you move even further away from the NNGP limit, you can't have perturbative expansions around your NNGP anymore. You get non-perturbative field theories, and you need to study some of those features in the non-perturbative field theories. This is where machine learning side has us this toolbox, black box architecture. It offers us this architecture, and using the architecture, we are going to study some stuffs. First, the NNGP. So the NNGP arises due to central limit theorem. Central limit theorem says that if you sum over infinite number of independent variables, that sum is always going to be a draw from some Gaussian distribution. And by the definition of the neural network outputs in the most commonly known architectures, the output is always a sum over n, the weight, n number of variables. These variables may be independent or may not be, and that's something up to us. That depends on how we choose the parameter distributions. If we choose the parameter distributions to be independent, then you get all these n variables independent. And your neural network output becomes a sum over n independent variables. Take n to infinity, your output is essentially a draw from some Gaussian distribution. But this output is also a function of the inputs. So this random variable is actually a draw from some Gaussian functional distribution. It's called a Gaussian process. Good question. So both of them are denoting the space of the inputs to the neural network. For us, they are just real numbers.
What does that mean?
So when we treat neural network, the inputs are treated as discrete points. But if we want a continuum field theory description, we need to treat the corresponding discrete points as draws from some continuous distribution. We choose that the inputs to the real numbers are drawn from just real line.
Then what is F?
F is the neural network output. So this just depends on what is your architecture, parameter distributions, and weight, and the choice of the original input. So going back one slide, let me go back. X is the original input before the whole black box appeared. And Fx is whatever appears out of the black box. So all the data processing happens in between. Good question. So anything that you see in this picture does not influence any of the expressions I had on that slide. These nodes do not correspond to the space points, does not correspond to the output points either. This is all about the machinery inside the neural network. And we just say that this final output, which actually depends on this choice of nodes and activation functions, can also be seen as a draw from a field distribution, where the field distribution actually knows nothing about the structure of the nodes and connectivities. So in one case, you are just effectively integrating over all these degrees of freedom and just getting the field configuration on the boundary. Right. You can also choose inputs as momentum space if you want. It's a choice. Now this sigma, this is the quadratic operator in the Gaussian action. And as expected, it depends on the choice of the two-point function. This, which you refer to as the kernel, machine learning community calls the propagator or two-point function as kernel. And there is a relation between the quadratic operator here and the two-point function. And this is the defining relation. Point to note that this structure, the structure of the propagator actually depends on the choice of our activation functions, number of hidden layers, choices of parameter distributions. So depending on what neural network architecture you are studying, the quadratic action will keep changing. So you have a ReLU single hidden layer, that action is going to be different than a ReLU network with 2 or 3 hidden layers. So we wrote down the PDF for the output density, and then we decided we are going to define a partition function, because then we can write down a J phi term and hit the partition function with derivatives with respect to the source J and pull out functions F. All right, so phi and F for me, they mean the identical thing. This is the field theory interpretation, phi. Then you can write down the correlation function in terms of the partition function and the action. And this way of studying correlation function is common to us. But in general, when people study neural networks, they treat it as some classical system. They don't write down e to the power minus action. When they are computing correlation functions, they will just take the expectation value over the product of the outputs and just calculate the statistical measure of the expectation value. It's just the statistical moment. So this was nothing special. We just said that using quantum field theory language, you have this alternate interpretation for the correlation functions. And this gives you the same values. At the end of the day, the correlation functions by this method match the correlation functions by statistical moment method. That was all. So this course, yeah. Oh, I see. Like what the different 2-point functions of neural network architectures will correspond to known field theory operators?
Yeah.
Awesome. That's a great question. That's a great question. The one-line answer would be that neural network architectures have different 2-point functions, and by that, different quadratic operators. And not all of them are the known derivative box term.
Yeah.
So you are actually getting a family of free field theories here. And you might have more than one architectures which have the derivative operator, the box, double derivative operator. But the rest of them, they're just going to be unique field theories. They may not have any quantum field theoretic interpretation at all. Any more questions on this? Because I will go to a new topic after. So it would still be quadratic in the sense, if you do a counting of the dimension, then just consider the dimension. So the dimension of this operator is going to be same throughout, as the form might change. Any more questions? Good. So, oh, I forgot to talk about the dictionary. Anyway, these are going to be some vectors. And I have denoted that dimension by d out in my very first slide. So each of them have this dimension, and fx and f of x prime has a separate dimension. These two dimensions are going to be completely different. And this happens by the way you construct the neural network architecture. And the dimension of this operator is going to depend on your choice of d in and d out. You can have 1-dimensional input space or 4-dimensional input space or 10-dimensional input space. So, and you can have a 1-dimensional field out of it. Any more questions? Let me go to the next topic. So if you move away from this NNGP limit, you are literally getting some perturbative expansions around your field theory. And one of the known ways to study such a field theory would be Wilsonian EFT approach. That's going to be my next 5 to 10 minutes. And as I noted, I forgot to discuss this dictionary. So this is a dictionary that relates various stuffs between the machine learning side and the field theory side. Important feature to note is right now, the output asymptotic neural network means this Gaussian process limit neural network. The output is corresponding to a free field because you do not see any interaction terms appearing here. The field density is completely Gaussian. Also note that there is this language in machine learning community for how we define action. So the notion of action is not completely unknown, but it's seen very differently. And they don't write down this partition function either. Now, coming over here, now we need some perturbative corrections to the field density. And these perturbative corrections are non-Gaussian terms. So now we know from the field theory side, non-Gaussian terms correspond to interaction terms, and their coefficients correspond to coupling strengths. Now we want to study field theoretic interpretation, but we also realized that if you're just adding some correction terms to your field density, you are writing down the effective action and not the full action in this case. You can get as close to the actual action as you can using the actual experimental statistical moments. And this probably answers your question from a couple of slides back, that this is no longer the NNGP, but even though you do not know the full action, you can study the correlation functions by running the neural network outputs and then predict what interaction terms are going to best describe a given architecture. So here comes some phenomenology. Note that the two-point function or the propagator can be the exact propagator in field theory language or the free propagator. And by this, I mean that there may be some architectures where the propagator, the functional form of the propagator as a function of inputs, remains invariant throughout any choice of parameter distributions, any choice of weight. It just doesn't care about what happens within the architecture. And in that case, even if you're describing a non-perturbative field theory via your architecture, there are some hidden corrections to the quadratic term in the action that show up in your exact propagator. So Wilsonian EFT says that in general, one can write down some interaction terms. Then you can compute the exact correlation functions by running the neural network on your computer. And then studying the structure of these correlation functions, you can determine which terms in these effective actions actually make sense versus which ones do not. For example, if you have parameter distributions which are mean-free, and then you compute the exact correlation functions by statistical averaging over the neural network outputs, all your odd point functions are going to vanish because it's a mean-free process. And in that case, if you have odd order interaction terms, these will give you some leading order non-zero corrections to your odd point functions. That's not what we want. So this experimental side then tells you that your EFT action cannot have any of the odd order interaction terms. You should start with the quadratic, go to sextic and higher order even point interaction terms. Also note that in addition to that, one can bring in some knowledge from effective field theory. There is this relevance of some operators versus irrelevance of some operators. And there may be some relative scaling between the couplings given as 1 over n. Why 1 over n? Because n is one of the features that control the non-Gaussianity. So if this controls the non-Gaussianity, and if some of these couplings or some of these interactions are more important over the others, then that scaling should show up in terms of this feature. So one can study the neural network correlation functions that you compute experimentally and predict that this is going to be more relevant than this, or this is going to be as relevant as this. We have found 2 instances, 2 different architectures for each of these examples. The first one, where this matters, this does not, and the second case, where both of these matters. So in the second case, where both of these matters, this one was discussed in a paper given here. They did not do Wilsonian EFT. They did a different non-perturbative 2PI approach that's inspired more by string field theory. For our purpose, we found that keeping the quartic interaction term gives us a very good definition for the weakly coupled field theories coming out of neural networks. Another feature, I have written a fully local interaction term, but in general, depending on the architecture, this interaction term can be as non-local as possible. Same goes with all the interaction terms. And so far, we have not found a theorem that lets us predict how to control the locality of these interaction terms. We are investigating and we find that so far it's a test and try sort of thing. You try out a neural network architecture, study how local or non-local the interaction terms are, and then decide if it looks interesting enough to you. But one of our ongoing works is to find out a first principle way to get field theories that are fully local out of neural networks. We want the usual derivative term in our quadratic action, but then we also want all of the interaction terms to be local. And there I will come to the random noise interpretation of neural networks later on, what we are doing to get such a local field theory out of neural networks. Good. Let me rephrase. If I understand your question correctly, then in particle physics, we never really get non-local interaction terms. In principle, yes, but right. So the deal here is if you actually compute the statistical moments of a given neural network architecture and predict the right quartic interaction term using that, it may be a bilocal one, fully non-local one, or fully local one. It depends on your choice of architecture. And you may want to ask that, I have a ReLU network. Can you tell me whether this is going to give me a fully local quartic interaction or a non-local quartic interaction? There is no way to know that. Unless you run the experiments with neural networks, compute its correlation functions, you can't predict that this architecture will give me a local quartic interaction or a non-local one. And what we are trying to do now is we want a way to engineer the architecture so that you won't even have to run those neural network experiments. You have the architecture, you look at it, and you say, oh yeah, this can only give you local interaction terms. Exactly. I'm using the notion of locality from physics and not the notion of locality from convolutional neural networks. No. So let's see. We found that this weakly coupled field theory for neural network output densities is useful to the machine learning community. They generally struggle with an exploding number of parameters the closer you go towards this NNGP limit, because you get very large number of nodes, large but countably finite number of nodes, and corresponding to each node you have weight, bias, and so on. But if you're studying that output density in terms of an effective action, then you would only get the relevant parameters. So you can initialize the neural network architecture, and that's all you need to do. Using experiments, you're predicting the effective action. Using the effective action, you're predicting higher order correlation functions, couplings, and so on. So there is this whole notion of overparameterization problem in machine learning community when your number of degrees of freedom gets too large. And the Wilsonian EFT way of describing the output density is getting us around that problem. No problem. So the thetas are stochastic variables. They get drawn from statistical distributions. And the hyperparameter n is called the weight. It's actually a discrete number. It gives you the number of nodes. But for our purpose, because I'm talking about 1/n scaling, so for our purpose, we are treating this as also as a continuous variable. Oops. So essentially, the whole story about the perturbative expansion around NNGP is that you do a phenomenology. You run neural network experiments and use statistical moments to predict the right effective action. Now, let me go over to the case where we are non-perturbatively away from this NNGP limit. this is the more interesting part, that there are two ways to move away from the NNGP limit, and both of the ways can be controlled by the user. You can reduce the number of nodes to a very small number, and now you are non-perturbatively away from the NNGP limit, or you can define parameter distributions right at the beginning for the neural network, and these are stochastic parameters that are correlated with each other. So now you have the neural network output, which is a sum over finite number of correlated random variables. You can combine them, both of them. So then you get finite number of correlated random variables, or it can be just a sum over finite number of independent random variables, or a sum over infinite number of correlated random variables, or a sum over finite number of correlated random variables. And all these three instances give us output densities that are highly non-Gaussian. And in this particular case, you cannot actually use just the statistical moments to predict what the action should look like. So that was good when you wanted to write down the EFT correction terms, but not good in this particular case. So then we had to give up on the hope of knowing the full structure of the action, but instead, we still wanted to study some properties. So we went back to the architecture, and we said we can just take the output of each of the node or neuron that goes into the sum and study their structure. We can study the symmetries arising due to this. We can study the correlation functions arising due to this. And we will use that information to study the symmetry or predict. We will use that information to predict the symmetry and the correlation function of the neural network, where it is treated as a value of a field over the input. So this side is the field interpretation. This is the value of the field over your input X. And here, this is the output of a particular neuron, ith neuron, where all of the hidden stochastic parameters, hyperparameter activation functions have left their imprints. And this knows nothing about those imprints. So this is a duality. This is the field space interpretation, and this is the parameter space interpretation. So in the case when you want to compute the correlation functions over the fields, you need to know the action, because you don't know actually what happens in between in each of the hidden layers. What defines your field? You don't know what defines your field. So you need to know the action. But we don't know the action. So we go to the other dual framework given by the architecture parameters. Here, we can write down correlation functions as expectation values over products of outputs. These are still the same neural network output by two different descriptions. As this expectation value, you can bring in the density over the neurons or density over parameter distributions and express the neuron outputs in terms of the activation functions and parameters. So each of these neuron outputs are aware of whatever mechanism goes in each of the hidden layers. They contain the form of every activation function. And this contains the choice of every parameter distribution at each node. But note, this doesn't have to be independent parameter distribution over each node. This can be as highly correlated as a single parameter distribution happening at each node. That's the most correlated parameter distribution you can choose for a neural network architecture. Same value of theta at each of the nodes. Now, using this expression, you can study symmetries, partition functions, and locality. So this is our motivation. And with this, I will go to the next studies, but please ask me any questions, because this is going to be the backbone of studying non-perturbative field theories. pH corresponds to, it's collectively the probability density over all the variables theta, variable or parameters theta. You can say that, but the only difference is the PDF over the parameters are never written in terms of the input space, whereas the field theory action is written over the input space. So in the case when the simplest case, all your parameter distributions are Gaussian, then this is just going to be a product over n Gaussian distributions. And it is blind to the choice of your input space.
Yeah.
Yep, it is not. It is not. This controls the action. You do this, you generate some action on the other side. I think so. I think so. One can think of this as the field is getting expressed over a basis of the neurons. Awesome. I think that's more meaningful when each of these neurons are independent variables. But if they're correlated, then this is probably not a good definition of a basis. Maybe this is a question we can discuss after I go over a few more slides. I'm just trying to give you guys as much flavor as I can. Yeah. Yeah, coming back to the story, if you have an infinite number of nodes, this is my bad. Here, if you go to infinity, and then if you have independent parameter distributions, then you get back the NNGP. Let me give you the interesting results. Let me talk about the symmetries aspect. I find symmetries very interesting. And you can actually engineer symmetries in these neural network output densities. You don't need to know the action, the form of the action. You can just choose parameter distributions with any symmetries that you want. And it can be shown that those symmetries become the symmetries of the action. When you have the NNGP, it's pretty simple because parameter distributions will govern the symmetries of the kernel or the two-point function. Take mean-free rotational invariance in your parameter distributions. Your two-point function would be rotationally invariant, and your one-point function will vanish. So you will have all the odd-point functions vanishing, and all the even-point functions, which can be written as products of the two-point functions by Wick's theorem, all of them are going to be rotationally invariant. And if your correlation functions all have the same symmetry, then your field density or output density also has that symmetry. So this is an alternative way of showing that your NNGP action has the rotational invariance in this case. The story is different when you are going to the weakly coupled field theory case or non-perturbative field theory case. Why? Because in the field theory language, you cannot study the correlation function, forget its symmetries. You need to know the action, and when you are non-perturbatively away, you do not know the action. We did find one interesting feature that even when you do not know the action, one can show that the product of the measure and this expression, which is the PDF, would be invariant under some transformation as long as the correlation functions are invariant. And let me show you this. If you want me to skip this maths, I can. Sorry. But essentially the story is this is the correlation function before a transformation. Phi is the transformation group. And this is the correlation function after the transformation. And all the steps in between can be shown to be absorbed in the symmetries of the action and the measure. So this product would be invariant as long as you can show these two are invariant. So we choose some parameter distributions which determine this invariance of the correlation functions. And this is easy to show by going back here. Any transformation on these neuron outputs can be absorbed as the transformation over the PDF of the neuron distributions. So that way you are controlling the symmetries of your correlation function, and that in turn controls the symmetries of your field theory action. We found that you can have SOD symmetry, SUD symmetry, octonionic, quaternionic symmetries in neural network field densities this way. An interesting feature. So there is a final layer, final output layer of the neural network, right after which you get the interpretation of the field theory. Any symmetries in the parameter distributions in that layer controls the internal symmetries of the field. There are also symmetries in the parameter distribution of the hidden layers. And we do not know what is the right field theoretic interpretation for that, because in field theory, we do not have such intricate structure in between. That's a new feature. On the other side, go right at the input of the neural networks. They get treated by some parameters of choice, and the symmetries of that parameter distribution will determine your spatial symmetries. We could engineer rotational symmetries and translational symmetries at that input layer, and this gave us Euclidean invariance in the neural network architecture. These are some demonstrations. To get rotational symmetry as the internal symmetry of the field, we needed the final weights and biases as draws from rotationally invariant distributions. And to get spatial symmetry on the Euclidean background, we needed the first linear layer weights and biases to be draws from rotational group SOD. So this was useful because we found that we can at least control one aspect of a field theory by engineering the architecture symmetries. And then we wanted to see what else. So this brings us back to studying correlation function, but the connected part of the correlation function. Why? Because we know that if you want to study the nature of the interactions that arise in a field theory, the best way to study that can be by studying the connected part of the correlation functions. Cumulant is another term for connected correlation function. And there is a way to get the expressions for all connected correlation functions. This technique is called cumulant generating functional. It's a whole subject of its own. So I will just give you the main result. This is the expression. This is the log of the partition function. And this can be expressed as a sum over product of currents times connected correlation functions. What we did find was one can also express this cumulant generating functional of the field theory side in terms of expressions on the architecture side. On the architecture side, this just becomes a logarithm of expectation value. And this expectation value is evaluated over the neuron contributions and the PDF of the neurons. And this alpha is a parameter that tells you how highly non-Gaussian your theory is going to be. So this is the definition. If alpha is 0, you can show that all of your neurons are independently drawn. So then at least your non-Gaussianity is due to finite weight. It's not because of the parameter distributions or neuron distributions. But if you turn on alpha as some large non-zero number, you're literally saying that the overall neuron distribution or overall parameter distribution in your architecture is so highly entangled, you really do not know what are the distributions associated with single neurons. So this is the other way of writing down the cumulant generating functional. And even if this remains unintegrable, in some cases, depending on your architecture, it can be very hard to integrate out. But nonetheless, you can study the structures here to some extent. For example, you can study the n scaling. And that may be very useful because there are two different cases. One, you turn off the parameter correlation. Your non-Gaussianity is due to small but finite width. And one can show that the field theory side connected correlation functions have a one-to-one correspondence with the neuron side connected correlation functions with a relative 1/n scaling. And this says that for r greater than 2, that is all your higher order connected correlation functions higher than the propagator, they're all going to vanish when you go towards the NNGP limit because they will keep on having relative 1/n factors. This shows a relative scaling between different connected correlation functions. And this says that your interaction terms, if you could write down an action, will have some relative scalings. On the other hand, if you have non-Gaussianity due to two combined effects, finite width and also parameter distributions are no longer independent, then this guy over here gets contribution from the connected correlation function of all of the nodes and all 1/n scale. And what do I mean by that? I have just hi, I have not summed over I. I'm just saying that you take a single neuron over here, and that neuron's connected correlation function was enough to tell us the field theory side connected correlation function. But in this highly non-Gaussian case, all the neurons are affecting, they're influencing the story of the field theory in a much larger sense. As you said, Flip, it's a way to interpret the field. One can think of the field as a sum over these terms, or it is written in this basis of neurons. And this particular case just shows us that the basis of a neurons is really showing up. You can no longer ignore it. I will keep the connected correlation function story just at that and go over to a simple extension. That's our goal. But before that, we want to have the local way of engineering field theories concrete. That's where we are now. Yeah, thank you for asking. That's exactly our goal, that we are trying to get neural network architectures giving us values of field over a lattice of input points. And we will just use that neural network architecture in this highly non-perturbative scenario to compute the correlation functions. But we will make sure that we get the right action for that neural network field theory. Okay. Great question. So currently, as of now, the neural networks that get defined.
Sorry, but I feel that we just warmed up and then getting.
I will get to that right at the end because that's an important question and that's the main motivation right now. So this is pretty simple. We found that there is a clever technique called the Edgeworth expansion, which is blind to the field theory story. It can just take the expressions of connected correlation functions and give you a series expansion for your partition function and also for probability distribution function. This probability distribution function is of the neural network output. I've written it as the field F, but output can be seen as field or as a sum over the neuron contributions. It doesn't matter. So what happens is you write down the PDF of the output as a field, but in terms of this expansion, this exponential function acting on this quantity. One may want to expand out this exponential function as a series sum. And then you have a bunch of expressions and relative 1/n scalings coming from this connected correlation function. So you get the PDF and the partition function as series expansions around the free field theory PDF and partition functions. And each of the terms, do you have a question?
Yeah, sorry, Karen.
Sure. Each of the terms in that series expansion will come with some relative 1/n scaling. And as you go towards the NNGP story, some of the terms in that expansion are going to be more important. Some will not be. But as you move further and further away in the non-Gaussian, non-perturbative story, more and more of the terms are necessary to describe your partition function and PDF. Good. Yes. And this is where the relative 1/n scaling in the connected correlation functions come up. Does that answer your question? Yeah. Then I will go to my last point and we'll finish up. And the last point is locality. and I will have a discussion with you after my talk about this. So we wanted to study locality. We found a way to control locality, a weak way to control the locality by studying the cumulant generating functional in terms of the architecture. So we are going to study by cluster decomposition technique, which says that take the original input points to your connected correlation function, make any two random subsets of these input points. Take these two subsets infinitely apart. And in doing so, if your connected correlation function vanishes, then your theory itself is local. There is a decay rate. The connected correlation functions have to decay exponentially or faster. And if they do, even if you do not know the action, you know that all the interactions in that action are going to be local. So this is a way to study the locality in your non-perturbative field theory. Right. Yes, as far as I remember from our study of this, it is obvious, but I do not have a proof here. And I can't write down a proof in 10 minutes for this. But essentially, the story is that you can control some aspects. You can control the structure of the connected correlation functions, at least the 1/n scaling of the connected correlation functions. And you can control the symmetries. And you can control the extent of the locality in your field theory without knowing the action. I have some discussion on locality afterwards, but that's better left for after the talk. So let me just summarize. Neural network field theories have the dual interpretation given by the architecture space, or one may treat neural network output densities in terms of architecture or in terms of field theory. The limit in NGP corresponds to a free field theoretic description. Moving small perturbatively away from this NGP limit gives you a Wilsonian EFT description, a weakly coupled field theory description. And moving a large amount away will just give you a non-perturbative field theory description. But non-perturbative field theories are interesting to us. So we went ahead and switched back to the other dual framework, neural network architecture framework. And we studied symmetries, connected correlation functions, a series expansion for the partition function and PDF, and locality by cluster decomposition technique there. And we also claim that in some cases, you are going to get neural networks where the resulting field densities corresponds to actual quantum field theories. This would be by the choice of the architecture such that your statistical moment or correlation functions satisfy the Osterwalder-Schrader axioms. So if you can, that's like a hit and trial sort of thing, then you are getting also the analytic continuation to the quantum field theory out of these neural network architectures. Let me just end here and take questions. And I have something more to say about how we are building local field theories out of neural networks, because there is a connection between that and the applications that you were talking about. The advantage is actually computations for lattice field theories.
Yeah.
At present, you need to use Markov chain Monte Carlo to get a handle on whether you're getting the right parameter distributions or the right architecture corresponding to the action. Now, MCMC is expensive in terms of compute resources, time and memory. And this way of constructing field theories won't require MCMC because you are just defining the architecture and not by guess. We are building up principles like symmetry, locality, 1/n scalings of correlation functions. So these principles will allow us to control what kind of action we want. Does that make sense? So this is a first principle approach to build quantum field theories on lattice without involving training using neural networks. So if you're not actually involving training, so when you are training, you do not have, you do not know the exact form of the parameter distributions. So if you do not know the exact form of the parameter distributions, in the non-perturbative field theory scenario, you actually have to first get the neural network. Sorry, let me rephrase. You do not know the exact parameter distributions corresponding to the neural network that gives you the desired action. In this particular case, we actually know the form of the parameter distributions. So we can study symmetries and correlation functions right by the architecture. We don't need to get the correlation functions. Sorry, we don't need to get the action. Good question. There's a two-step answer. First, we did study Wilsonian renormalization group flow when we had perturbative expansion around the NNGP in this case, because when we were computing the corrections to the correlation functions from the EFT action, the corrections were often divergent. So we needed a cutoff scale. And we noticed that the actual statistical moments do not care about any choice of cutoff scales. So the choice of cutoff scales was just a mathematical construct. And these couplings had to run with that cutoff scale. So there was the Wilsonian RG flow arising there. And we experimentally tested that the couplings that you write down for a given architecture actually show you the RG equation that you predict. Like experimentally, they show you the same RG equation. On the other hand, if you go to this non-perturbative field theory, I do not know the answer about RG flow, but I have something very interesting to say about training. Suppose you are starting with a neural network with infinite number of nodes, independent parameter distributions, or weakly coupled parameter distributions. So you are getting a weakly coupled field theory, you are writing down an EFT action, and then you are training. Training is increasing the amount of non-Gaussianity, your interaction strengths are changing. So there has to be a description of RG flow there when your interaction strengths keep changing. But we have not studied that. Because it's starting from a free theory. If you start with n infinity, IIT parameters, you're starting from an NNGP limit, free theory. And then you are training, and training is causing parameters to talk to each other. And that's breaking the independence assumption in Central Limit Theorem. Your theory is getting non-Gaussian. It's getting perturbative or non-perturbative corrections in the output densities. So if you keep increasing the number of hidden layers, the computation of the propagator gets more and more difficult. Because each time you're appending a new layer, the kernel gets an integration over a new sets of variables and new activation function. Kernel is the propagator. But on the other hand, every time you append a new layer, you get a new NNGP, a new quadratic operator in the free field theory corresponding to that network. So that's the advantage. You just append a new layer, you get a new field theory out of that. And same goes for the non-Gaussian scenarios. You do not know how much the interaction terms are going to change. You append one layer, you might shift from a local quartic interaction to a bilocal quartic plus a completely non-local sextic interaction in your EFT. So yeah, go ahead. Any more questions, or should I say something about the locality aspect? Thank you. So it's actually similar to the notion that you brought up, that you have a lattice of space points. Yeah. And then you are talking about Gaussian field densities or non-Gaussian field densities at each of the space points. We found that since it's hard to control the locality, we don't always have a first principle approach to build local field theories in neural networks. We found that an easy way is just define a lattice of space-time points, and at each of the space-time points define a single neural network. So it's going to be an infinite number of neural networks at each of the given lattice points. What is the advantage? Each of your neural network has a single input point. So the action corresponding to that neural network is going to be completely local. even when that theory is non-perturbative. So if you have EFT, all your quartic and sextic interaction terms are going to be local by definition. And you can control the non-Gaussianity by choosing parameter distributions and weight for each of these neural networks. So you might have the lattice where a few of your neural networks at points you have chosen, those are non-Gaussian and rest of the steps are all Gaussian. This is all great, but then what about the derivative term in your action? That's where we are stuck right now. If we have that answer, we will give you the scale.
Too local.
It's too local. Yeah. So we have got two non-local, we have got two local. We want something in between. It's good, but then if you're defining the space-time to be on a lattice, and then how do you define the neighborhood of each of the points? Right, exactly. It's
not a grid.
These are two independent.
Yeah.
That has no orders.
Right. The inputs don't even know about each other. So where is the ordering? Right. And that's what we are trying right now. It's interesting, actually. We are trying that, suppose we can embed some correlation by choice of the first linear layer parameter distributions. We have tried various things, but the major obstruction is the formal definition that your space is a collection of infinite zero-dimensional points, and you're trying to define some four-dimensional manifold or one-dimensional manifold out of that. And then how do you properly define it mathematically?